Math 1325, we are doing our review for test number 4 today. The review has 20 questions ranging from section 6.6 through all the sections of chapter 7. And there's only 6 sections this time instead of the usual 7. 5 sections in chapter 7 and the one from 6.6. So first 3 problems come from 6.6. Find dy for the given values of x and delta x. Y equals 2x cubed minus 5x and then we're told x is -3. Delta x, which really is the same thing as dx, it's the change in x, is 0.2. X is changing by 0.2 at any given moment in time. So what's happening to y at that point? So remember that one of the symbols for derivative is to put dy over dx, the derivative of y with respect to x. And you're really doing the derivative of y, but that equals 1. So you just get a 1 dy over dx on this side. On this side, it's all about x, so you just do the normal power rule. 2 times 3 is 6x, decrease the exponent by 1, and the derivative of 5x is just 5. Then if you multiply both sides by dx, you get a slightly different format that starts to resemble what we do in chapter 7 actually with the integrals. So it's just an equivalent way to write this. dy, the change in y, is equal to the derivative of x times the change in x is what that's saying. So, and that's what we're looking for is dy. So we can plug -3 in for x. And we can plug 0.2 in for dx because that's the same thing as delta x. And then it's just a matter of calculating this. -3 squared is 9. 9 times 6 is 54. 54 minus 5 is 49. 49 times 0.2 is 9.8. So whenever the x is changing by 0.2, the y is changing by 9.8. So whatever it doesn't tell us what the x and y are, but if you get things like price and demand, when price changes a little bit, what does it do to demand? For example, in a business setting, round to the nearest tenth, but it came out exactly to the tenth, so no need to round anything. Okay, so another thing we did in section 6.6 was we could use what's called a linear approximation to do things like square roots or logs, approximate them. This is how they used to do it way in the past. It's now kind of obsolete using a calculator, but in fact, part B says what is the value found using a calculator. So the square root of 60 is, and how far, 4 decimals, 7.74596. So we have to add 1 to this 9. Think of adding 1 to 59 and turn it into a 60. 7.7460. So what would the linear approximation give me as an answer for square root of 60? Square root of 60. So the function is square root of x. And then what you want to do is you want to, well, first of all, the idea behind it is if you take f of x and add a little bit, add this little delta x, the change in x, if x changes a little bit, this is approximately equal to the original f of x plus what happens is the change in y. A little bit of change of y, adding, because f of x is y. So it's kind of like you're saying that if I add a little bit to x, then a little bit gets added to y, which kind of makes sense. And since dy is the same thing as what we just had a second ago, dy is equal to the derivative, this parentheses the derivative, times d of x. So I can keep the f of x here, and then I can change dy to be f prime of x times dx. So what would f prime of x be if the original f was square root of x, which is the same thing as x to the 1/2? It would be x, it would be 1/2 x. You'd bring the power rule down, 1/2 x, and then decrease the exponent by 1, negative 1/2. So then if I want to write these in a way where I'm going to plug numbers in, I'm going to change x to the 1/2 back to square root of x for f of x. And then I'm going to change this to 1/2 and put this x to the negative 1/2 in the bottom and change it back to a radical. Okay, so the trick is you try to get close to 60 with whatever the closest square root that comes out evenly is. The closest square root that comes out evenly is 64. So could I change 64 to have 60 in it? What if I think of this as 64? 64 minus 4? 64 minus 4, that's how you get 60 to happen. So the 64 is the x that we're going to work with exactly, and the 4 is the little bit of change in x. I'm changing x slightly. So that you would just want to make sure that this expression you have right here equals this, using a number that comes out nicely. So the 64 is chosen for a reason. If I work with one I can do exactly and then add or subtract a little bit, that gets me back to the original problem. So now what happens is I get to have square root of 64. The x is 64. Whoops, 64. And then the dx is basically negative 4. We're going down by 4, a little bit of negative change. So this would be 8 plus 1/2 times 8 times negative 4. And plus a negative is the same thing as minus. 2 times 8 is 16. So if I do 1/16 times 4, that's 0.25. So 8 minus 0.25 is 7.75. Just like if you had $8 and take a quarter away, you have $7.75 left. So notice, see, that's pretty close. 7.75, that's the approximation using a differential. It's really a linear approximation. Round to 4 decimals, but as needed, because it wasn't needed, it came out exactly. But if you round this to 2 decimals, this would be... Did I write that right? No, wait, I didn't finish that. Or I know what happened. I typed the other one wrong. These two should be close, and there's obviously they're not. This, I think I had an extra 3 accidentally typed there. Square root of 60. Yeah, it's not 73. It's 7.7456. So I could tell it was wrong. It was just a slight typo. But see, if you round this to 2 decimals, it would be 7.75 also. So this was a way in the past, before calculators were around, where they could approximate these radicals pretty closely. What is the absolute value of the difference? So the first one's bigger. If you do the bigger one first and do a difference, then you won't have to worry about absolute value. The absolute value of the difference is 0.004. That means it's off by a 0.004 difference. So that's a pretty close approximation. Okay, for the final thing in section 6.6, it's very similar to the first problem. It's just a business setting of it. So I have the demand function given to me in relation to price, demand versus price. It's negative 3p cubed minus 2p squared plus 1464. And there's a part A and part B, but once you do one of them, the other one's very similar. It's going up from $2 to $2.23. This is what amounts to the X variable, because the number, the variable in the parentheses is like X normally. So the price is changing. This is delta P or dP. The change in price is 223 minus 2. The change in price, it's going up by 23 cents. It started at $2 and it went up by 23 cents. Okay, so the change in demand based on a change in price is what they're looking for. So how is demand changing when price changes? See, this is that idea that if you do the derivative of demand, it will equal the demand function's derivative times the change in price. You know, if you have like dy over dx, and then you move the dx over here. So same idea as this right here. dy equals f prime of x. This is f prime of x right here, or y prime. So dy equals f prime of x times dx. D of D equals D prime of P times dP. It's the exact same concept. And the question's asking for how demand is changing. So I need to do the derivative of the demand function, which is easy as a power rule, negative 9P squared minus 4P. And the derivative of that's nothing. And then the P is the original price, not what it changes to. So you put 2 in for P's. Each P gets a 2. And dP gets that 0.23. Two squared is 4. 4 times negative 9 is negative 36. Negative 4 times 2 is negative 8. So that's negative 44. Negative 44 times 0.23 is negative $10.12. So if the price goes up, the demand goes down. That makes sense. And actually, it's not money, it's 1,000 pounds. So I messed that up. It's not money. So it's going down by 10.12 thousandths of pounds. But they want it left in thousands of pounds. So you just, whatever answer you get, you put there. I forgot my negative. Negative 10.12. So what would happen if you started at $6 and increased to $6.20 for part B? The only real difference is you're going to put 6s in these slots where the 2s are. And then your $6 is going up to $6.20. So that means the dP, or the delta P, would be 620 minus 6, or 0.20. So this will change to 0.20. For part B, I just have to recalculate. So 6 squared is 36. 36 times negative 9 is negative 324. 4 times 6 is 24, so minus 24. That's negative 348 times 0.20. So now the demand is going down by 69.6 thousandths of pounds. So that shows you inflation right there. When inflation affects things, it can really hurt. Negative 69.6. So before, there was actually a bigger difference here. This was up 23 cents. This was only up 20 cents, but it made a bigger difference in the demand. The demand went way, way down just because the prices were higher, even though the change in price wasn't as much. Okay, so now we're in chapter 7, and 7.1, the first thing we learned was indefinite integrals, basically antiderivatives, the backwards version of derivatives. When there's no numbers on the integral sign, then you just put a plus c at the end. So I want to do the integral of 10x cubed plus 10x squared minus 3x plus 2. So remember, you go 10x, increase the exponent by 1, and divide by that new exponent. Just go term by term. 10x, increase the exponent by 1, divide by that new exponent. 3x to the first, increase the exponent by 1 to a 2, divide by the new exponent, and a constant turns into a linear, and the nothing turns into a constant because the derivative of a constant is nothing. So nothing here reduces except for the 10/4. So final answer should be 5/2 x to the 4th plus 10/3 x cubed minus 3/2 x squared plus 2x plus c. That was just teaching how to do the antiderivative steps in a polynomial. 5/2 x to the 4th plus 5/2 x to the 4th plus 10/3 x to the 3rd minus 3/2 x squared plus 2x plus c. Okay, what if you get negative or decimals or fractional exponents? So just slight variations, what we just learned on number 4. Now we want an indefinite integral of negative 10t to the negative 3.5 minus 9t to the negative 1. So negative 10t, add 1 to this exponent, negative 3.5 plus 1 is negative 2.5. And then divide by negative 2.5. Minus, now here's this is a special case, but if you forget this, here's the way to remember this. If you add 1 to that exponent, it would be a 0, and if you tried to divide by 0, that's undefined. This is the special case that's 9 ln of t. If you do an antiderivative of a negative 1 exponent, that's ln, because the derivative of ln is 1 over whatever the variable is. So if you ever divide by 0, oh yeah, right, that's the time. Yep, that's when it's ln. So does negative 10 divide by 2.5 exactly? Yeah, it's positive 4. Positive 4t to the negative 2.5 minus 9 ln, and then don't forget the absolute value around t because natural logs have only a positive domain. And because the original problem had a negative decimal exponent, I would just leave my answer that way too, to the negative 2.5. You could make it negative 5/2 if you wanted to, but there's the absolute value tool button, and then t, and then don't forget the plus c also. 4t to the negative 2.5, 4t to the negative 2.5 minus 9 ln of absolute value of t plus c. Okay, and then a business setting. The marginal profit in dollars of brie cheese sold at a cheese store is given by this p prime of x. So we're given the derivative function. The profit, quote, profit is negative 70 when no cheese is sold. So that's going to help you get the c value. Find the profit function. So we're going from a marginal profit or derivative, and we need to go back to the original, which is an antiderivative. And even though the original one is a product, you might want to, since there's no exponent here, you might want to distribute that x in there. Otherwise, you'd have to use integration with substitution, which isn't even taught till the next section. So I would put 40x cubed plus 60x squared if you distribute the x in. That way the integral of p prime t dt will equal regular profit. So I need to do an integral of 40x cubed plus 60x squared, which would be 40x, increase the exponent by 1 to 4, divide by 4. So that'll be 10x to the fourth. 60x, increase the exponent by 1, divide by that new exponent. 60 divided by 3 is 20. X cubed, and then plus c. This is the profit function. And then they say if you don't sell any cheese, you lose $70 because you have costs like your rent and your utilities and your workers and insurance and all that kind of stuff. So if your business is open, you're not selling anything, you're losing money actually. So the profit, if you want to call it profit, to lose money is negative 70 if you don't sell anything, if x is 0. So this helps you get what the c value will be. In fact, when it's all zeros, that's nice because then c is literally this negative 70, only because 0 times 10 and 0 times 20, they're all zeros. So c is negative 70. So the profit function would be 10x to the fourth plus 20x to the third minus 70. And then you can plug in any t amount. I don't know why I switched to x. These should have been t's here. You can plug in any t amount, which is the number of product you sell, and you can figure out what your profit will be. And more importantly, we want to know how many things of cheese we need to sell before we start making a positive profit. So 10t to the fourth. Oh no, these are x's. Okay, I don't know where the t came from. So, okay, 10x to the fourth plus 20x to the third minus 70. That's that in general. And then find the profit from selling 300 pounds of cheese. X is in hundreds of pounds, so be careful about that. X is in hundreds of pounds. This is 300, so that means you're just plugging 3 in. Plug 3 into those x's. 3 to the fourth power. 81 times 10 is 810. 3 cubed is 27. 27 times 20 plus that 810 minus the 70. So we would make a positive profit of $1,280 if we could sell 300 pounds of cheese. Okay, so now, see on number 6, there was no exponent up here. So then I could distribute that x in and avoid what we're about to have to do here. Because now there is an exponent there, I can't just distribute the 7 in, although that's just a 7 anyway. But that's the main difference here. So number 7... indefinite integral, but I'm going to have to use substitution now. 7x minus 8 to the 9th power. So if you have some kind of parenthesis part with an exponent or a denominator or exponentials, that's when this substitution stuff can happen. I'm going to take the inside of the parenthesis and do the derivative of it. And conveniently enough for me, the derivative is 7 dx, which happens to be all the other stuff in the problem. That's what you hope happens. So everything's accounted for. This part equals u. The exponent can stay there, and the rest is du. du equals the rest of the stuff 7 times dx. So now we can do an antiderivative of this pretty easily. Increase the exponent by 1 and divide by the same amount. And then finally plug the stuff that u was set equal to back in. Put 7x minus 8 back in for u. Or you could write this 1/10 7x minus 8 to the 10th power plus c. And see, if you took the derivative of this, you would get back to the original problem, because you would do the exponent times the constant. 10 times 1/10 is 1. You would write the base, decrease the exponent by 1 to 9, and then you'd multiply by the inside, the chain rule, which is 7, and that's where the 7 comes from. So 1/10 7x minus 8 raised to the 10th power plus c. And we need the plus c because it's indefinite still. There's no numbers over here. Okay, when there's a fraction, usually the denominator is the u substitution, and also you always want the higher exponent to be the u substitution, because a derivative of a higher exponent will drop you down to a lower exponent. So the top's got x to the third, x to the third minus 2x. The bottom's got x to the fourth. And the derivative of a fourth power is a third power. Minus 4x squared plus 3. So this time I'm going to let u equal the entire denominator. The derivative of u with respect to x would be 4x to the third minus 8x to the first, and nothing for the 3. And that isn't quite what's here right now, but it's only off by a constant. There's a 4 here, and then there's an x cubed. If I factor out the 4x cubed, then 8 divided by 4 is 2. And this would be dx right here. Whoops. 2x, yeah. See, there's the x cubed minus 2x. But I have an extra constant right here. If there's an extra constant in the problem, you just pull it out front. But if there's an extra constant in the du statement, then you have to insert it in the problem, but you can't just put it there for free. So we have to balance that out with a 1/4. But don't mess up like I did on the homework, where the extra constant, if it's over here, you just pull it out front. There won't be a 1/4 if the extra constant was in the problem. So 1/4 is the extra constant that I need. Now with this 4 here, then all of that is du. See, that's the key, is to get that to match up. And then the bottom is u. So you can either write 1 over u du, or you can write du over u, however you want to write it. It's really the same thing. X over 2 is the same thing as 1/2 x. And this is the one we just had a second ago. If you have 1 over u, that's u to the negative 1, and the antiderivative of that is ln of the absolute value of u. Since if you tried to increase exponent by 1, you would get 0. And now we can plug the stuff that u is equal to back in, which it's 4x, x to the fourth, x to the fourth minus 4x squared plus 3. And say this was just like x to the fourth right here. X to the fourth is never negative. So if you knew this was never negative, then you could drop the absolute value bars, but because there's more stuff there, it's maybe not so easy to tell if that is never negative or never zero. It's definitely never 0, but it may be that that's never negative. But if you're not sure, you can always leave the absolute value bars in. 1/4 ln And then I'm going to hit the absolute value of x to the fourth minus 4x squared plus 3. And then on the outside, plus c. Okay, so here we have marginal cost, which is derivative. And then we want the regular cost. So what substitution should be used to determine the regular cost? You're going to be probably best off putting the entire denominator as u, because the derivative of e is nothing. So if you ever have a constant, if you can include that in your u statement, it's good because the derivative of it doesn't matter. The derivative of 4x squared is 8x, which is a constant off of the 32x that's there already. So I would do the whole denominator. The whole denominator, 4x squared plus e, and that way the derivative of that would be 8x. Okay, so the only issue is that there's a 32x actually there, not an 8x. So this is where there's going to be an extra constant in the problem, not in the du statement. 32x over 4x squared plus e. So we're letting u equal the denominator. The derivative of that is 8x dx. But I need to think of 32x as 4 times 8x. And now I have an extra constant in the problem, not in du. An extra constant in the problem is what just comes out to the front. It won't be 1 over 4. And then I'll have 1 over u, like we like, so that we can get a natural log of u for the antiderivative. 1 over u. This is all u, and there's no exponent to it. And then you can put du in the top or make it 1 over, and then this will be du because all that's left here now is 8x dx, which is what du is equal to. So this will be 4 ln of the absolute value of u plus c. And then I can plug this stuff back in for u. Okay, so this is not quite the answer yet because it says find the cost function given that the company incurs a fixed cost of 10,000 even if no units are built. So the 10,000, the company has found the marginal cost in thousands of dollars. Okay, so $10,000 means that the cost is actually 10. And then if no units are built, that's 0 for x. So the x, if the x is 0, this is what the cost function equals c of x. So what they're doing here is they're letting you plug 10 in for the cost function answer. And then you get to plug 0 in for x so that you can find this plus c at the end. Well, this is nice because 0 squared is 0, times 4 is 0, plus e is e. The natural log of e is 1. Times 4 is 4. So the constant is 6. So now I can rewrite this answer with a 6 right in this slot here. So that would be the, well, actually I would want to do it with this, not with that u there. So 4 ln absolute value of the 4x squared. Now see here, the absolute value might not be needed because 4x squared is always positive or 0, but then when you add e, it's going to definitely be at least e every time, but plus 6. Therefore, the cost of producing 5 units is blank. So now let's plug 5 in here. 5 squared is 25, times 4 is 100. 100 plus e, and then take the ln of that, times the 4 in front, plus 6. Okay, so this was in thousands of dollars, round to the nearest dollar, so I think I have to convert this to thousands. So this would be, move the decimal over 3 times, 24,527.96, so 528. 24,528. The cost of producing 5 units is almost $25,000. The company will seek a new source of investment income if the cost is more than $15,000. So yes, they should seek a new source of investment income because they've gone over their $15,000 limit. Okay, so that's 3 of the 6 sections. We got 3 more to go. Now we're into section 7.3, where we do these approximations with rectangles and using left endpoints, right endpoints, midpoints, and even averages. Okay, approximate the area under the graph of f of x and above the x-axis with rectangles using the method with n equal to 4. And we've got the function 6x plus 5. We are going from x equals 5 to x equals 7. And they want 4 rectangles. So 7 minus 5 over 4 is the width of each rectangle. Each rectangle should have a half width, or 0.5. Okay, first for left endpoints. So we're going to go, starting from 5, let me make a number line here. There's 5, 5.5, 6, 6.5, and 7. There's really 5 spots here. The left endpoints use the 4 first ones, and the right endpoints use the 4 last ones. So it's whatever this graph is doing. This is a line. So for the left endpoints, you're coming from the left side to make the rectangle. There's one rectangle, here's a second rectangle, here's a third rectangle, and here's a fourth rectangle. But you touch the graph at the left side where the first 4 numbers are. So I need to do 0.5 for the width times f of 5 plus f of 5.5 plus f of 6 and f of 6.5. Not f of 7. And technically they're all multiplied by 0.5, but so then I can pull that out as a GCF. So f of 5 is easy. 30 plus 5 is 35. 6 times 5.5 plus 5 is 38. 6 times 6 is 36, plus 5 is 41. You can already tell what's happening. This is linear, so these keep going up by 3. The last one must be 44. So 35 plus 38 plus 41 plus 44, and then times a half. 79 is the left approximation. Left endpoints will give you an answer of 79 for the approximation of the area. The good news is when you switch to right endpoints, you get rid of the first one. The next 3 are all the same, 38 plus 41 plus 44. But then you're tacking on f of 7 instead of f of 5. The last one's f of 7 instead of using f of 5 for the first one. So now what's happening is the rectangles are going like this. The first one is here. It's at this height, so it looks like this. This is the first rectangle. Here's the second one. Here's the third one, and here's the fourth one. They're all sticking out. They're overestimations. 7 times 6 is 42, plus 5 is 47. So it'll be 38 plus 41 plus 44 plus 47 and times a half. That estimation's 85. Whoops. The average of 79 and 85 is 82. And if you don't know that, just add it up and divide by 2. So then midpoints, now it turns out on linear ones that the midpoint answer is the same as the average of those two, just because of the linear line balances out the above distances. These below emptiness slots are exactly the same as these above ones if you have a linear function going on. But if you didn't know that, what you would do is you would just cut each of these numbers in half. Halfway between 5 and 5.5 is 5.25. Halfway between 5.5 and 6 is 5.75. Then 6.25 and 6.75. So I need to do 0.5 times f of 5.25, f of 5.75, f of 6.25, and f of 6.75. So maybe I'll do this here quicker. 6 times 5.25 plus 5. Whoops, I didn't put a parenthesis at first. Just put a parenthesis. Okay. So the first answer is 36.5. So what I'm going to end up with is 0.5. The first answer is 36.5. That was plugging 5.25 in. Now I can quickly plug in 5.75 and get 39.5. Now we know this is linear, so they're going to keep going up by 3, but 6.25 and then 6.75. There's the other two going up by 3. 42.5 and 45.5. So same process, you're just plugging in different x values. Add them up and multiply by half, and it is 82. If I had any function like a quadratic or an exponential or a log, then that wouldn't be true. But if you get a linear, the average for part C always matches the midpoint approximation. Okay, then the other thing we did in section 7.3 is we approximated these areas using geometry, and this actually showed where definite integrals come from, which was the next section, 7.4, where we could just do this with a calculus calculation instead of using geometry. So what if I have 1 plus x dx? See, now you guys know how to do this more easily. You could just do the antiderivative and the fundamental theorem of calculus here. But what they want you to do is get a graph of 1 plus x. So it has a y-intercept of 1. It has a slope of 1. It starts here, goes here, here, and here. Here's the line. And then all we care about is from 1 to 3. This is the area right here. And this is a trapezoid in geometry. So the trapezoid area formula is 1/2 times the height times the two bases added together. And the height is the distance between the parallel sides. So the height here is the distance between 3 and 1, which is 2. B1 is literally f of 1. B1 is f of 1. F of 1 is 1 plus 1, or 2. Plus, you can see in the graph it's at 2. And then f of 3 is going to be 4. And half of 2 is 1 and cancels, so the answer here is 6. So this was the geometry way of knowing that that area is 6. Geometry tells me that that answer is 6. What calculus tells me, this is the part you didn't know until the next section, but I showed it to you just to prove to you that this works. If you did the antiderivative, you would get x plus x squared over 2. And if you evaluate that from 1 to 3, like we're going to do in the next section, big F of 3 minus big F of 1, you would get big F of 3 would be 3 plus 9 over 2. And big F of 1 would be 1 plus 1/2. So that would be 3 plus 9 over 2 minus 1 and minus 1/2. 3 plus 9 over 2 minus 1 divided by 2. The answer is 6. So that shows that the geometry confirms that the fundamental theorem of calculus works. And that way, when you get one that doesn't have a geometry formula that goes to it, then you can only do it the calculus way. But this is not part of problem number 11. I just did this extra to, again, review that for you. That's what section 7.4 it was born from. So 11, I did it 2 different ways and got 6 both ways. I did it a geometry way and a calculus way. Okay, so what if you don't get a linear one? We're going to go from 0 to 50, and they want rectangles that have width of 10, which really means there's 5 of them. So if you do 0 to 50, and they can either tell you what the number of rectangles should be and you figure out the width, or they can tell you the width and you figure out the number of rectangles. If they want the width to be 10, then 50 minus 0 over 10, this is the number of rectangles. There's 5 rectangles. So the 5 rectangles, the widths are 10. So 0, 10, 20, 30, 40, and 50. There's actually 6 numbers here. However many rectangles there are, you're going to have one more number than that on your number line. So the left endpoints, I'm going to take my width of 10, and then I need to do f of 0, f of 10, f of 20, f of 30, and f of 40. And then for the right endpoints, you're going to have your width of 10, but it's going to use the last 5 instead of the first 5. So it'll do f of 10, f of 20, f of 30, and f of 40 and 50. So they always share all of them the same except the first and last one. So f of 0 is easy because you just get the 273. Okay, the rest are not easy. F of 10, I got to plug a 10 in. 1/10 times 10 squared minus 10 times 10 plus 273. So the f of 10 is 183. And that will go here as the second answer, and here is the first answer. Now I'm going to change to f of 20 by quickly pressing second enter and changing these two 10s to 20s. So this is where the graphing calculator helps speed this way up, because this takes a long time to do by hand. F of 20 is 113. F of 30 is 63. F of 40 will be the last one here on the top. 33. And then the bottom still needs f of 50. $23. So the left endpoints, I'm going to add 273 plus 183 plus 113 plus 63 plus 33 and multiply by 10. Since that's the width, 6650. 6650 is the left endpoint approximation. The other one is 183 plus 113 plus 63 plus 33 plus 23 times 10, 4150. The first one's overestimating, the second one's underestimating. So if we average them, that'll give us a better approximation. So 4150 plus 6650 and divide by 2. So 5,400 would be a better approximation than either one of those two, and midpoints might be better too. But they didn't ask for the midpoint, so we don't have to worry about it. Okay, 2 sections left. We have section 7.4 and 7.5 to go, and these are very similar to each other. 7.4 is when you're doing the fundamental theorem of calculus, but you're going between a curve and the x-axis and always cognizant of which one's higher. And then in section 7.5, same deal, you're going between 2 curves and you always have to worry about which one's higher. Now, if they just say do a definite integral, then you don't care about if you cross the x-axis or not. This one says evaluate the definite integral. So I don't need to draw a graph. I don't need to worry about does it drop below the x-axis. That's immaterial if you're just doing definite integral. The only time that matters is when you're talking actual area. So if they say area between a curve and the x-axis, or in section 7.5, area between 2 curves, that's when you got to worry about which one's higher than the other one. But if it's just find the definite integral, you just go straight away to your calculating. 5x, increase the exponent by 1, divide by that new exponent. 6x, increase the exponent by 1, divide by the new exponent. And 8x. And then we evaluate this from 0 to 5. And you can reduce this to 3. So big F of 5 minus big F of 0. So I need, for big F of 5, there's going to be a 5/3, 5 to the 3rd power, minus 3 times 5 squared, plus 8 times 5. Big F of 0 is literally all zeros. Because 0 cubed is 0, times that is 0, 0 squared is 0, times that is 0, and 8 times 0 is 0. So it's nice when big F of 0 is there and if it's all zeros. Okay, so 5/3 times 5 cubed minus 3 times 5 squared plus 8 times 5. So I typed it in here. It's a big messy decimal, so now we got to worry about sometimes they want decimals, but often they like fractions. So math, enter, enter. It's probably going to be 520 over 3. Rather than 173.333. But if they say round to the nearest 10th or 100th, then I would do a decimal. Here it just says simplify, so if they don't ask for a decimal, definitely don't put it. They want a reduced fraction whenever they just are generic like that. And that was a definite integral, so is this one. Go from 7 to 4. For here's negative exponent 7n to the negative 2 minus n to the negative 3. Definite integral, we don't care about area right now. So 7n, increase the exponent by 1, negative 2 plus 1 is negative 1, and divide by that new exponent. Increase this exponent by 1 and divide by that new exponent. Evaluate from 4 to 7. You can clean this up by making it negative 7n. Actually, what I'm going to do is put negative 7 over n. So 7 divided by negative 1 is negative 7. The n to the negative 1 can drop to the bottom. This double negative here can be a plus. The 2 is going to stay in the bottom. I'm going to move the n to the negative 2 to the bottom. And then there's nothing left in the top, so you got to have a 1 there. This would be the best format to do if you're going to be plugging numbers in. If I was just putting a plus c at the end, I probably would have left these negative exponents here. But with plugging numbers in, it's much easier not to have negative exponents. Big F of 7 minus big F of 4. Okay, so negative 7 over 7 plus 1 over 2 times 7 squared. That is big F of 7. Big F of 4 is negative 7 over 4 plus 1 over 2 times 4 squared. So negative 7 divided by 7 right here is negative 1. 7 squared is 49 times 2 is 98, so plus 1 over 98. Negative 7 over 4, but then it's going to get this negative and turn into positive 7 over 4. 4 squared is 16 times 2 is 32. It's 1 over 32, but then it's going to get a negative and be minus 1 over 32. So this would be hard without a graphing calculator because you'd have to get common denominators. But here I can just type it like it looks. Negative 1 plus 1 over 98 plus 7 over 4 minus 1 over 32. Negative 1 plus 1 over 98 plus, I typed that wrong, I didn't put 7 over 4. Try that again. Negative 1 plus 1 over 98 plus 7 over 4, over I'm just hitting division, minus 1 divided by 32. There it is. And then it's a decimal, so math, enter, enter. Okay, they're probably going to want a decimal then if it's this messy of a fraction. Let's see what they're asking for. Type an integer or a simplified fraction. Okay, good thing I've got a graphing calculator because that would be very hard without one. 1143 over 1568. Now we do area. See how it says area between the x-axis and the function. So now we have to slow down a little. We can't just do the derivative straight out like this. We might have to break it into separate parts, in fact. So f of x equals 50 minus 2x squared. And we're going from 0 to 8. So I'm going to set this equal to 0 because 0 is the x-axis. And I want to know, does it cross 0 at any point? And if it does, then we're going to have to break it into separate pieces. So add this negative 2x squared over, divide by 2. And take the square root. It actually does cross the x-axis twice. But luckily, plus or minus 5, luckily only once in this interval. The other time is at negative 5, that doesn't matter. So that means I'm going to have to do two separate integrals. I'm going to have to go from 0 to 5. And then I'm going to have to go from 5 to 8. Now you could take a look at a graph and decide, is the function above or below the x-axis? And if you knew it was above, then it would just be that function. If it was below, you could do the negative version of the function. Because literally what you'd be doing is 0 minus it. But their suggestion anyway is just do the function out. 50 minus 2x squared. Do that for both of them. One of these answers is going to be positive and one of these answers is going to be negative. The one that's negative, you can take the absolute value of it if you care about area. So 50x is the antiderivative of 50. and then minus 2x to the third over 3. This one will get evaluated from 0 to 5. Luckily, it's the same antiderivative, so you don't have to redo the work. And then that one goes from 5 to 8. Big F of 5 minus big F of 0 is going to be nice because big F of 0 is going to be all zeros. 50 times 5 minus 2/3 times 5 cubed. That's big F of 5. Big F of 0 is 0 minus 0, because this part will equal 0 and this part will equal 0. So 50 times 5 minus 2/3 times 5 raised to the third power. The first answer is positive. So that means this graph must be above the x-axis at first. Math, enter, enter. It's 500 over 3. And that kind of makes sense because if you have a 50 y-intercept, and you're negative 2x squared, you're going to be coming down like this. So it makes sense that it's above the x-axis first and then it's below the x-axis second. This part's going to be below. So technically what you could have done, if you use your section 7.5 knowledge, you know how you do the upper curve minus the lower one. We technically could have done 0 minus f of x right here. If we would do 0 minus f of x rather than just putting f of x here, then it would come out positively. But it can get confusing. You might mess up the double negatives. So their suggestion is just do the derivative or antiderivative. It's going to come out negative, and you can just get rid of the negative at the end. The fact that it's always 0 in this section is why that's true. So now I need big F of 8 minus big F of 5. Big F of 8 would be 50 times 8 minus 2/3 times 8 cubed. And big F of 5 will be 50 times 5 minus 2/3 times 5 cubed. 50 times 8 minus 2/3 times 8 cubed. Math, enter, enter. That part is 176 over 3. 50 times 5 minus 2/3 times 5 cubed, as we know, is 500 over 3. But it's minus it now, actually. So 176 minus 500 is negative 324 over 3. So this area up here is positive 500 over 3. This area down here is negative 324 over 3. If I just did a definite integral all the way from 0 to 8, the negative would cancel out part of the positive. And you'd only get about 176 over 3 for the answer. But instead, what I'm going to do is 500 over 3 plus the absolute value of negative 324 over 3. If I care about area, then I absolute value the negative answers, the parts that are negative. So instead of subtracting, you end up adding, and you get 824 over 3, which actually divides by 3. 824 divided by 3 comes out to exact, oh, I guess it doesn't, okay. Okay, yeah, I was thinking since 24 divides by 3 that might, but it doesn't. So it's going to stay 824 over 3. Integer or simplified fraction. Okay, so now we have a derivative function given to us, and we want the total profit, which is regular profit, for the first 4 years. So this is an integral from 0 to 4 of the derivative function. And that's going to take a substitution, a u substitution to finish it. t squared plus 2t plus 4 because that parenthesis has a 1/5 power. So I would let u equal the parenthesis part that has an exponent. And then the derivative of that would be 2t plus 2. Okay, so there is an extra exponent over here, or extra constant, I mean. So 5t plus 5 versus 2t plus 2. What I'm going to need is a 5/2 times 2t plus 2. Because if you distribute 5/2 into there, all the 2's cancel and you get 5t plus 5. So the 5/2, this is an extra exponent. I keep saying that, extra constant in the problem, not in the du. That's where this is the one I messed up in the homework. So this, you got to pull that to the outside. The 5/2 comes to the outside. This parenthesis becomes u to the 1/5. And then the 2t plus 2 and the dt, they turn into du. And that way everything's accounted for. So then the antiderivative would be u to the 6/5 divided by 6/5. Actually, not a plus c. We're going to plug in 0 and 4 eventually. So flip that around to 5/2. Flip this fraction to make it 5/6. Plug the stuff that u is equal to back in. T squared plus 2t plus 4 to the 6/5 power. And now you get to evaluate it from 0 to 4. And nothing here cancels, so this right here is 25/12. So big F of 4 minus big F of 0. So I'm going to get a 25/12. 4 squared plus 2 times 4 plus 4 to the 6/5 power. That's big F of 4. Big F of 0, well, 0 squared is 0, and 2 times 0 is 0, but the 4 will still be there. So big F of 0 is not going to be all zeros. It'll have the 25/12 in front. And then these two parts will go to 0, but the 4 will still be there to the 6/5 power. Okay, 4 squared is 16, plus 2 times 4 is 8, plus 4. The inside of this parenthesis right here is 28. 28 raised to the 6/5 power is a messy decimal times 25/12. Still a messy decimal. And let me check if that's what they want for answers here. Nearest dollar, okay. So we can just stay in decimals. Okay, so I got 113.5921711. Okay, 4 to the 6/5 power times 25/12. So now I need to do 113.5921711 minus this answer. Okay, so I calculated all this and got 102.5962718. Okay, so round to the nearest dollar. These are in thousands of dollars. So you have to change this to thousands first. Move this over 3 times. And then if this digit was a 5 or higher, you would add 1 to this 6, but it's not. So mine will be $102,596. That's for the first 4 years. When it says find the profit in the 7th year, that's from year 6 to 7. Because the first year is from 0 to 1, basically. So now I got to repeat this from 6 to 7 if I want the 7th year. And all that should change is what you're plugging in. The rest should be the same. So I can take what I had right here and do it from 6 to 7. So 25 over 12. T squared plus 2t plus 4. To the 6/5 power. And from 6 to 7. So big F of 7 minus big F of 6. Okay, 7 squared is 49, plus 2 times 7 is 14, plus 4. The inside of the parentheses, 67, raised to the 6/5 power, times 25 over 12. So big F of 7 is 323.6298157. 6 squared is 36, plus 12, plus 4. The inside is 52, raised to the 6/5 power, times 25 over 12. That one is it's actually positive, but I'm going to minus it. 238.76066623. So now do 323.6298157 minus this answer. 84.8691536. Move the decimal over 3 times. So it'll be $84,869. And there's a 1 here, so I don't have to make it $70. 84,869. Okay. And then remember this, how the answer was that it just increases without bound. Strangely, that if time goes on forever, your profits increase forever. Okay, so now we're up to the final section. Now we're doing area between curves, and now it is about area, so we do have to worry about which one's above the other one. So this is number 17. There's 4 problems left. We're going to go between -2 and 1. The first curve is linear, y equals 9x. And the second curve is quadratic, x squared minus 10. Do these 2 graphs ever cross each other? Set them equal to each other and solve and see if they equal each other. So I would move the 9x over and get it in this order: x squared minus 9x minus 10. If it's going to factor, there's going to be 1 positive and 1 negative. Multiply to 10 and subtract a -9, so that would have to be -10 and +1. So x equals -1, they meet each other there, and they also meet at 10. But my interval is going from -1 to 2. So we're starting right where they're crossing each other, and then there's going to be 1 graph entirely above the other because of that. So x squared minus 10 has a -10 y-intercept. And then it would be at -9 at both 1 and -1. And at 2, it would be -6. So this is the parabola. We're drawing this much of the parabola right there. The line goes to the origin and has a slope of 9. So apparently it's like that. Here's the line. And then if we connect this up. So this is the area. It starts where they meet each other, and they would eventually meet each other again. If you kept curving up here, they'd meet each other when x is 10. But we don't care about the rest of this parabola going up like that. So we're just drawing a vertical line right here at 2, because that's where the interval stops at. So I do have an area, and from -1 to 2, the line is always above the quadratic. So then I can just do one integral from -1 to 2, put the line first, and minus the quadratic second. So this is why in the last section you could think of, if you know that your graph's entirely below the x-axis, you could do 0 minus your function and you would get a positive answer instead of just doing it and then switching it to positive. So I could clean that up and change it to -x squared plus 9x and plus 10. Be careful about that. So the antiderivative of that is -x to the third over 3, 9x squared over 2, and positive 10x. And then we're evaluating from -1 to 2. So big F of 2 minus big F of -1. So that's -8 over 3 for 2. 2 cubed is 8. Plus 2 squared is 4. 4 divided by 2 is 2. Times 9 is 18. And 10 times 2 is 20. This is big F of 2. Big F of -1. -1 to the third is -1, but then times this -1 would make it positive 1 over 3. -1 squared is 1, so then you would just get 9 halves. And 10 times -1 is -10. So I have a -8 thirds. I could combine this together and get 38. And then I'm going to put a -1 third, a -9 halves, and a plus 10. Okay, so here it's easy. -8 divided by 3 plus 38 minus 1 divided by 3 minus 9 divided by 2 plus 10. This came out to exactly 40.5. Math enters 81 over 2. Whichever way they wanted. I think this one they took it both ways. 40.5, since it's exactly that. And 81 over 2. Those two are equivalent to each other. Let's be sure. Yeah, this says simplify, but I think I remember in the homework I put it in as a decimal and they took that answer, but just to be safe, I'll put 81 over 2. Okay, then they don't give you where it's going between, so now you have to decide for yourself where do these lines graphs cross each other, and probably they're going to cross twice and enclose each other. So we got a line 5x, and we have a quadratic x squared. So when do these equal each other? There's a GCF of x. So they equal each other at 0 and 5. So this line goes through 0, 0, so does the quadratic. But the line is rising faster at first, because when x is 1, the y would be 5 on the line. So here's the line. It's going through 5, 10, 15, 20, 25. 1 squared is only 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. And 5 squared is 25. So it takes all the way till 5 for that quadratic to catch up to the line. But then they crisscross, and then forever after, the quadratic will be above the line, although we don't care about that, because this part will be open. It'll never close itself up again. And yes, this line continues this way forever, and this parabola continues that way forever, but they're all open over here. The only enclosed part is this little wedge right here. From 0 to 5, and the line's always above the quadratic. So I would do 0 to 5, I only need one integral. The line would be above the quadratic, so you'd have to subtract it in that order. And there's nothing to clean up, so I'm ready to do the antiderivative. 5x squared over 2 minus x to the third over 3. From 0 to 5, at least big F of 0 will be all zeros. So the answer is just going to be whatever big F of 5 is. So 5 squared is 25, times 5 is 125 over 2. 5 squared, that can't be squared, that's cubed. 5 cubed is 125 over 3. This part is big F of 5. Big F of 0, both of them are 0. So whatever 125 over 2 minus 125 over 3 equals, so probably math, enter, enter, it equals 125 over 6. That's how much area would be there, 125 over 6. Or if they do want decimals, about 20.8. It says integer simplified fraction, so we definitely need 125 over 6 and not the decimal. Okay, here's this consumers and producers surpluses. So I have a supply curve on number 19. Supply curve is q squared plus 15q. The demand curve, 1056 minus 19q minus q squared. Well, a negative q squared goes downward, a positive q squared goes upward. And this supply curve definitely goes to the origin because there's a plus 0 at the end here. So supply curve is doing this. The demand curve has a y-intercept of 1056. And it's got a negative q squared, so it's going down. They would actually crisscross each other over here again, but we don't care about negatives, the side of this graph. So this spot right here, this is q, and this is the equilibrium point. I'll just put f of q since I don't have another letter to use. So the point of equilibrium is q comma f of q. If I could find those two values, then the consumer's surplus is this top area and the producer's surplus is that bottom area. So I have to set these equal to each other and solve them for when they cross each other. They're going to cross each other once in the positive range, once in the negative range. So add this q squared over here, it'll be 2q squared. Add this 19 over, it'll be 34q. Subtract this 1056. These all divide by 2, luckily. And even then, it's still a little challenging. So, unfortunately, that's a 17 and not an even number. Half of 1056 is 528. So if I could somehow figure out what multiplies to 528 and subtracts to 17, those are the two numbers we're going to need. We could do completing the square, but with a 17, it's going to get messy. I don't know if the graphs here would help me decide what they are, but it's definitely not graph C because this supply curve is not going through the origin. And the supply curve is supposed to be the solid one. So the one coming up through the origin is supposed to be solid. So that eliminates graph D. And then the y-intercept of the demand curve is over 1,000, where this one's under 1,000. So it's definitely graph A. I don't know if you can blow this up and get a hint of what the Q might be. This is 50, so it looks like it's going 5, 10, 15, 20. So it looks like it's a little bit past 15, so that's still maybe not enough to be able to guess and check. 15. 528, does it divide by 16? Yeah, 33. So I just got lucky there. I just used the graph to try to save me some time on doing quadratic formula and completing the square. But apparently 16 times 33. 16 times 33 is what makes this happen. And if I want the 17 to be positive, it would need to be Q. Can I fit this in? Q plus 33 and Q minus 16. That's how it would factor. 33 and the 16. And if you do 33 minus 16, that's how you get 17. So positive 33 minus 16, that's how the 17 happens. And 33 times negative 16 is negative 528. So the point that they cross each other over here in the negative side, that would be negative 33. But the only one I care about is this positive 16. So the ideal quantity where supply and demand will balance each other is 16. I can plug 16 into either one of these two, and they're going to both give me the same answer. So 16 squared is 256. 15 times 16, I'm plugging it into this top one, plus 256. So this is apparently 496 right here. 496, that's the horizontal. So the point of equilibrium is a quantity of 16 and a price of 496. 16 and 496 are the two key numbers. 16, 496. Okay, so the last two things is we do the consumers and producers surpluses. So two similar processes. The consumers is always the top one. And in that area, if I did the area of this top wedge, it would be this downward demand curve above the horizontal. So I would need to do an integral from 0 to 16. The consumer surplus goes from 0 to 16. The demand curve would be the top function, and the 496 would be the bottom function. That would just be a constant, but you're always going to use that 496 in both parts. So the demand curve is 1056 minus 19Q minus Q squared. So I could rewrite this as 0 to 16. I'm going to put the negative Q squared first, then the negative 19Q. 1056 minus 496 is 560. So antiderivative, negative Q to the third over 3 minus 19Q squared over 2 plus 560Q. Evaluate from 0 to 16, and luckily plugging 0 in makes all zeros, so I just have to do big F of 16. So negative 16 cubed over 3 minus 19 times 16 squared over 2 plus 560 times 16. Whatever this is, that's the part C answer. Negative 16 to the third power over 3 minus 19 times 16 squared over 2 plus 560 times 16. 5162.666 repeating. They want nearest hundredth for dollars and cents, so I rounded it up to 67 cents. The consumer's surplus would be $5,162.67. Now for the producer's surplus, very similar. You're going to go from 0 to 16, but now the horizontal is above the supply curve. So where's my graph? Down here, It's the horizontal 496 that's above the supply curve. So this is going to be minused. So you need to minus your Q squared plus 15Q. But that entire thing gets minused. So put the negative on both parts. So from 0 to 16, I'm going to do a negative Q squared first, a negative 15Q, and a plus 496. So negative Q to the third over 3, minus 15Q squared over 2, plus 496 times Q, evaluated from 0 to 16. Plugging 0 in produces all 0, so I just need big F of 16. Negative 16 cubed over 3, minus 15 times 16 squared over 2, plus 496 times 16. Negative 16 cubed over 3, minus 15 times 16 squared over 2, plus 496 times 16. 460, $4,650 and 66660 cents for that one too. 4650 and 67 cents. So the consumer surplus is a little larger than the producers. This is like when you have, like in real estate, you have a buyer's market, a seller's market. So that means the economy is just a little better for consumers right now than it would be for producers. And then we did one of these in the homework last time. So we've got these two curves. They're on a metal sheet. You cut them out. So there's no where it goes between. So apparently these two cross each other twice. And then we'll just go from wherever the two cross points are. So one function is a radical, the other one's a linear one. 6 square root of x. The other one is x over 3, or 1/3 x. So when does 6 square root of x equal x over 3? I could multiply by 3 first just to get rid of the fraction. When does 18 square root of x equal x? Square both sides to get rid of the radical. 18 squared is 324. 324x equals x squared. So make this side 0. Factor out an x. So they apparently equal each other at 0 and 324. And if you plug in a number like, say, 100, because 100 comes out evenly in a radical, 100 is between 0 and 324. The square root of 100 is 10 times 6 is 60. But 100 divided by 3 is 33.3 repeating. So apparently the radical graph is going to be above the line until we get to 324. 324 is finally when the line will catch up. And this is the only enclosed portion of the graph then. So the radical is above the line. I would need to do an integral from 0 to 324. Put the radical first and the line second. That would be the above curve minus the below curve. So I could rewrite this as a 6x to the 1/2 minus a 1/3 x, just to make it easier to do the antiderivatives. So for the first part, it'd be 6x, increase the exponent by 1 to 3/2, divide by 3/2. 1/3 x, increase the exponent by 1, and divide by that. Evaluate from 0 to 324. You can flip this around and make it 2/3. That's 12 over 3 or 4x to the 3 halves. This you just multiply the 3 and 2 and get 16x squared. So big F of 324. So this 3 halves right here, the half part of that is a square root. Does the square root of 324 come out exactly? It's 18. So the square root of 324 is 18, then raise it to the third power, and then multiply by 4. 23,328. Okay, so 324 squared divided by 6. 1 6 is the same thing as dividing by 6, so minus 17,496. And then luckily 0 to any power is 0 times 4 is 0. 0 squared is 0 times that is 0, so big F of 0, both of those are 0. So whatever 23,328 minus 17,496 is, this will be the answer, 5832. 5832. Okay, so we've answered every question. Now we'll submit it and see how well we did. I only missed one problem. Okay, that's weird. 17, what happened on that one? I had 81 over 2. That's weird. 9x and x squared minus 10. Oh, I think I know what I did wrong. It's from -2 to 1, but I did from -1 to 2, I believe. I just wrote the problem down wrong is what happened. Here's my 17. Yeah, see, that's exactly what I did. So there's a brain cramp mistake. I wrote the wrong problem down. It was supposed to go from -2 to +1, not from -1 to +2. -2 to +1. And that would actually change it a lot, because then you would have to back up over here. There would actually be 2 different areas. So we're already over an hour and a half here in this video, so let me just set this up and then you could do it yourself, hopefully better than I did. But it should have gone from -2 to -1. From -2 to -1, the parabola would be above the line. So then you'd have to put the x squared minus 10 minus the 9x. That would be one problem to do. And then you would add to that from -1 to +1, where the line would be above the quadratic. This is what should have happened. I didn't realize I had the wrong x values down. So at least I was doing the process right, and I got everything else right, which is good. So I missed only number 17 because I wrote the problem down wrong. And I'm sure if I had written it down right, I probably would have done it right, but I'm not going to spend another 15, 20 minutes redoing that whole problem. Okay, so hopefully this helped you to go through your review, and now you can do all 20 of these. This fourth test is very, very, very similar to this review. So if you do this review, I just did the review and got a 95, so that would be pretty, if you can get a good grade on it the first time like I just did, then you're pretty confident you could get a good grade. Obviously, the brain cramp mistakes can happen. They happen to me a lot, so I put the wrong starting values here, which made this wrong. But that's it for the fourth unit. And all we'll have left after we take the test at the end of this week is next week we'll be reviewing and taking the final.